Hello everybody. So inside this video we're going to be looking at another momentum problem, and in this particular example I feel like this is going to complete the series of types of collisions and bring some light as to what it means to be an inelastic collision. So originally when we did our first problem we had two objects that collided, then they stuck together. That's an inelastic collision, and how an inelastic collision is defined is where you lose the most amount of kinetic energy. Because when we went to the next problem, we did a perfectly elastic collision. That's a collision where no kinetic energy is lost. Kinetic energy is conserved. Then in our third problem, we would have solved the problem. This was an elastic collision, but we could not use the formula that we derived, assuming that the collision was perfectly elastic. That's because there's some loss in kinetic energy, whether it goes to sound, whether it goes to heat, whether it goes to or friction, it's lost. And conservation of kinetic energy, in that case, it doesn't hold. So when we get to this case where we have an explosion is an inelastic, well, it's a reverse inelastic collision. You have a case where you have two objects that are initially together and then they separate. So kinetic energy is not conserved, but it doesn't decrease. In this particular case, kinetic energy actually increases. So again, whenever you're doing momentum problems, read the question, interpret it. At this level, they're going to tell you exactly whether it's inelastic and whether it's perfectly elastic. If they do not say otherwise, then it's probably just a regular elastic collision. And in this case, when you're dealing with explosions, you always know that these are inelastic collisions all the time. Okay, so to carry on with the problem, we have an internal explosion that breaks an object initially at rest into two pieces. One which is 1.5 times the mass of the other. If 555 joules is released in the explosion, how much kinetic energy does each piece acquire? So here I've drew it, and I'm going to let my bigger piece be A and my smaller piece be B. So here's the object. Before it explodes, let's say this is some kind of firecracker, or those are usually the best examples. And it explodes and it breaks into two parts, one part being bigger than the other. So having already accounted for that, I have mass of A is equal to 1.5 times the mass of B, and I like working with fractions. So here it's 3 over 2B. Now, writing out what they said that if the kinetic energy released in the explosion is 5,500, meaning that the kinetic energy released in the explosion, this is right here, this is where the explosion happens. So the kinetic energy of this and the kinetic energy of this, when I add those two together, that must be the total energy that was released inside the explosion. So kinetic energy of B plus the kinetic energy of A is equal to 5,500. And I know that kinetic energy is 1/2 mb vb prime squared plus 1/2 mb ma va prime squared is equal to 5,500. Now, I'm kind of stumped on a few things, because here they're asking me to figure out what this and this is, but I have no information about them other than this, other than about their masses. Well, I do know that conservation of momentum also holds. So what happens when I apply that? So doing it down here, total initial is equal to total final. Initial momentum is 0 because it's initially at rest. So this is 0. So now I have mass of A, VA final, plus mass of B plus VB final. Now I know that the mass of A is equal to 3 over 2 times the mass of B. So MA is equal to VA, and I can make that substitution here. 3 over 2 MB plus MB entire thing is equal to 0. So again, I'm going to work on this. I'm going to factor out this MB because it's the same on both sides. 3 over 2 VA plus VB prime. Now by the zero product property, either MB is equal to 0 or this expression here is equal to 0. And when we're dealing with masses, unless explicitly stated otherwise, which is very, very rare, at least not at this level, the mass is never going to be 0. So automatically, this must be true. This is equal to 0. So, or I can solve this for VA just for consistency, since I already have the mass of A in terms of the mass of B. I'm going to have final velocity of A is equal to minus VB prime times 2 over 3. I just subtracted from both sides and multiplied by the inverse. So now this gives me something. Now I have a relationship of the mass of A in terms of B, and I have a relationship with the velocity of A in terms of B. So now I'm going to go ahead and make my substitutions up here. So I have 1/2 MB VB prime squared plus 1/2. Substituting, I end up with 3 over 2 MB. Over here I'm going to end up with negative 2 over 3 VB prime all squared, and this is equal to 5,500. Simplifying this more, I'm going to get 1/2, well, I may as well work it out. I get 3 over 4 multiplying those, squaring this. This becomes a positive inside this bracket. This becomes 4 over 9, and these cancel. This becomes a 3. All of these become 1s. And if you get confused, you can just go back and you'll see what I did. So there's no shame in pausing the video and going back. So multiplying these two together, I get 3 over 4. Squaring negative 2 over 3, I get 4 over 9. 3 over 4 times 4 over 9, things cancel. And I end up with 1 over 3 MB VB prime squared. Okay, so just to show you that again, 1 over 2 times 3 over 2 times 4 over 9 MB VB prime squared is equal to 5,500. And all of this simplifies to just 1 over 3. Because here, and this is a 2 here, this cancels, so this becomes 2. This is 1, this is 1, this becomes 1, this cancels with this becomes 3, plus 1 over 3, MB VB squared is equal to 5,500. Combining these together, 1 over 2 plus 1 over 3 is equal to 5 over 6. So this becomes 5 over 6 MB VB squared is equal to 5,500. But here I can do something really interesting. If I pull out a 5 over 3, this just becomes 1/2 MB VB1 squared is equal to 5,500. Now the reason that I did this is because they asked for the kinetic energy of each piece, and I realized that this is just a fraction of it. The kinetic energy acquired by each piece is just a fraction of the original kinetic energy. So if I add those fractions together, I should get the original thing. And this helps me to figure out what fraction of that total kinetic energy this is. So this is what I end up with. And this is 5,500. Now what this tells me that the kinetic energy acquired by B after the explosion is 3/5 of the total energy released by that explosion, which is 5,500. And 55 divided by 5,500 divided by 5 is 1,100. 1,100 times 3. This gives us 3,300 joules. And by this identity up here, kinetic energy of B plus kinetic energy of A is equal to 5,500. Both of these are kinetic energies after the explosion. Rearranging that, kinetic energy at A is just equal to 5,500 minus the kinetic energy released at B, which is 3,300, and this becomes 2,200 joules. Now, again, this is an example of not a perfectly inelastic, this is an example of a reverse inelastic collision where you have an object that is initially one and then there's an explosion and it separates. Now, there's energy needed to generate this explosion, so most of the time you're going to have zero momentum initially and you're going to have zero kinetic energy initially. But when you get to more advanced problems, you'll see that you have maybe an object moving through the air like a cannonball and it explodes midair, and that will require a bit more an advanced analysis. Nevertheless, so when we look back, the kinetic energy acquired by each piece, kinetic energy of B is 3,300, kinetic energy of A is 2,200, and this is only possible because I was able to write my mass of A in terms of mass of B, velocity of A in terms of velocity of B, and if I wanted to go the other way, if I wanted to let B be the bigger part, it really wouldn't have mattered once you were consistent with your algebra. So I do encourage you to pause this video at any point where you don't understand, to ask questions in the comment, and to make sure that you grasp this, because grasping this idea, I feel like this is really going to tie everything that you do when you're doing momentum problems together. So have a wonderful day, and I hope to see you soon.